So, what if I told you there was a single key that could unlock the entire internet? Not a physical key, of course, but a quantum one. In this explainer, we're going to dive into an algorithm that could literally change everything we know about our digital world. You know, every time you send a private message, or buy something online, or even just check your bank account, you're putting your trust in a secret. A huge mathematical secret that keeps your entire digital life, well, private. But what happens if that secret is about to be blown wide open? To really get a handle on what's at stake, I want you to picture something. Imagine all of our online data, and I mean everything, is stored inside one massive digital vault. Think of it like a modern-day Fort Knox, but instead of gold, it's protecting our information. So what's actually inside this vault? We're not talking about abstract bits of code here. We're talking about your life, your bank details, your private DMs, your company's most confidential data. The stakes, they really couldn't be any higher. Okay, so what's protecting this vault? The lock is this absolutely brilliant invention called public key cryptography. And the most common type, one you use dozens of times a day without even thinking about it, is called RSA. Now, the real genius of this lock isn't just that it's strong, it's how it works. It's built on what mathematicians call a hard problem. And that's just a fancy way of saying it's a task that's super easy to do one way, but almost impossible to do in reverse. Yeah, it's called an asymmetric system, and for a good reason. There are two different keys. There's a public key, which anyone can use to lock up information and send it to you securely. And then there's a private key, which only you have to unlock it. And its security, it all hinges on that one-way street. Let's make this really simple. Imagine you take two massive prime numbers, multiplying them together. For a computer, that's a piece of cake. It's just basic arithmetic, and it's done in a fraction of a second. But what if I flip that around? What if I give you this number, the result, and ask you to find the two original prime numbers that made it? Well, that simple reversal is ridiculously hard. For a normal computer, we're not talking minutes or hours. We're talking billions of years. And that, right there, is the integer factorization problem. The sheer, brute force difficulty of working backward is the very bedrock of our digital security. It's the one-way secret that pretty much our entire online world is built on. So we have this nearly unpickable lock. Sounds pretty good, right? But what if there was a master key? A key that wasn't forged from metal, but from the weird and wonderful rules of quantum physics. Well, that key is an algorithm, and its name is Shor's algorithm. The difference between the two approaches is just staggering. A classical computer would try to break the lock by guessing every single possible combination, which, as we said, could take eons. But a quantum computer running Shor's algorithm, it doesn't guess. It finds a hidden mathematical pattern, and it solves the exact same problem in maybe a few hours or days. And this really gets to the heart of it. Shor's algorithm is so incredibly clever because it's not a brute force attack. It totally reframes the problem. It changes it from factoring a huge number to finding the period, or kind of the hidden rhythm of a special mathematical function. So how does this period finding trick even work? Okay, look, we're going to skip the deep, heavy quantum mechanics for now and just focus on the core idea, because it is absolutely fascinating. All right, here's the basic idea in 3 steps. First, the algorithm just reframes that hard factorization problem into a hunt for a hidden repeating pattern. Second, it uses the really unique properties of a quantum computer to, in a way, listen for the rhythm of that pattern. And then finally, it uses that rhythm to calculate the original prime numbers with surprising ease. It's a total game changer. Now, the core engine that actually finds this rhythm is a tool called the Quantum Fourier Transform, or QFT. The best way to think of it is like a superpowered lens that can instantly see the main repeating frequency in a really complex signal. It's the secret sauce that makes Shor's algorithm possible. So this master key exists, at least in theory. And that brings us to the next crucial chapter. What happens now? Well, what happens now is a global race to build a brand new, much stronger digital vault before the old one can be cracked open. And why is it a race? Because the second a large-scale quantum computer is built and working, our entire cryptographic infrastructure becomes vulnerable. We're talking secure financial transactions, government secrets, corporate data, and the personal privacy of, well, everyone. This threat is exactly why scientists are working like crazy to develop something called quantum-resistant cryptography. These are completely new kinds of digital locks, built on totally different hard problems, problems that even a powerful quantum computer running Shor's algorithm just can't solve. So that's where we are today. The quantum master key is being forged in labs around the world as we speak. And the big question for all of us is, are we going to be ready to build a better lock before the old one finally breaks?